Welcome back to Worldview Theoric today. What would we see if we approach the speed of light? Let's embark together on a spaceship which accelerates away from Earth, moving faster and faster. What would we see when constantly accelerating? What optical effects would occur? And if we try to exceed light speed by bending spacetime like in sci-fi movies, what would we see? Answering these questions will lead us to explore many fascinating phenomena of our universe and immerse ourselves at the heart of special and general relativity. Our spacecraft is initially at rest. Take off. Once launched, we begin to accelerate. We imagine that its propulsion system allows us to accelerate constantly as long as we wish. As we gain speed, we move away from Earth by accelerating more and more. One would think that the speed would eventually become unbearable, however, this is not the case. Speed has no effect on our body. When two trains cross, it is impossible to feel whether it is our train or the other which is at rest. Similarly, inside the spaceship, we cannot feel its speed but only its acceleration, the thrust of the reactors which presses us against our seats. If this thrust is reasonable, it will be perfectly bearable all along our journey, even when approaching the speed of light. There is nonetheless a risk associated with very high speeds, a collision at high velocity. A mere speck of dust would cause colossal damage if it hit us. Fortunately, our ship is equipped with a force field that repels dangerous objects and allows us to roam freely through space. As we accelerate, a first optical effect, aberration of light, appears. The stars in front of us, which we get closer to, seem to gradually move away. The sky contracts before us. To understand, think of this common situation: you are in a car driving at high speed and it starts to rain. The rain falls vertically from top to bottom, but as the car moves forward, you receive raindrops on the windshield from face on. The rain does not appear to fall from above but from the front, as if its trajectory were tilted. The more you accelerate, the more the rain seems to come from face on. Our spaceship, the optical effect, is perfectly analogous. The star's light comes from a certain direction, but as we accelerate, the light rays appear to come more and more from the front. Their direction seems different when we are in motion. This is the aberration of light. As light focuses in front of us, its intensity increases, while behind us, the sky seems to widen and becomes darker. The aberration of light results in another strange phenomenon. Let's imagine we are moving through an immense grid representing the fabric of space. Ordinarily, we would see a straight grid made up of straight lines converging in front of us due to perspective. However, by speeding up, the aberration phenomenon distorts the image of the sky around us. As the days go by, the grid seems to contract forward, and the straight lines bend. If we were to go past an object, it would appear to be slightly angled in our direction. This is called Terrell-Penrose rotation. As we move very quickly, images of objects seem contracted in front of us, and perspective is strongly distorted. We often hear that the further we look into space, the further we look into the past. Indeed, the light we receive from a distant star must travel billions of kilometers. This journey is not instantaneous, and it takes some time for light to reach us. As a result, we see the star as it was in the past when it emitted this light, perhaps several thousand years ago. Who knows how it might have changed since then? Looking out from our spaceship, the same phenomenon is at work. As we move away from Earth, the planet's light takes longer and longer to reach us. If we could zoom in with a telescope, we would see people on Earth evolving in slow motion. This is the Doppler effect. Each tick of the clocks on Earth takes longer and longer to reach us. We receive light rays in slow motion, and their intensity seems to weaken as the image of the planet shifts towards red color. In front of us, it's the opposite effect. The ship catches up with the light, and the stars seem to get brighter. They shift towards blue color, and their clocks seem to tick faster. With precise enough equipment, we could measure the aberration and Doppler effects since the start of our acceleration in space. However, if we decided to end our journey and return to Earth, these effects would have had no impact. They are only optical illusions due to the way we receive light while moving. After several hundred days, however, as the reactors push us ever faster, the ship begins to approach light speed. At such speeds, some phenomena will no longer be mere optical illusions, real physical effects will kick in with irreversible consequences. Special relativity comes into play. A first consequence of relativity is known as time dilation. Our universe is a huge four-dimensional fabric called spacetime, made up of 3 dimensions of space and 1 dimension of time. Inside spacetime, all bodies trace a trajectory since they all advance towards their future. For takeoff, our ship was moving in the same way as Earth towards the future. But by picking up speed and zooming away from Earth faster and faster, our trajectory gradually deviated from that of the planet. The axis we call time is no longer aligned with the time axis of people on Earth. If we decided to turn around and come back, our clocks would have measured a different time, and we would have aged less than Earthlings, because our trajectories in spacetime would have been different. Another key consequence of special relativity is called length contraction. When a body moves close to light speed, its length gets contracted in the direction of its motion. From the spaceship's perspective, the entire universe is moving backward. For us, the universe is contracted along our direction of motion. As such, the length of the journey to reach our destination is shorter than expected. We are not talking about optical effects anymore, but of a physical and concrete phenomenon. If we tried to reach a distant star, the journey would genuinely seem shorter to us. It would take less and less time the faster we move. Thus, contrary to popular misconception, it is, in fact, possible to travel thousands of light years in just a few seconds. And in the case where we would move almost at light speed, the journey would even seem instantaneous to us. For the people on Earth, however, several thousand years would have passed. Length contraction is a very real phenomenon, however, visually, it would be difficult to see. To understand why, imagine that we crossed the orbit of a planet. As it moves very quickly towards us, the planet's length is contracted. But remember, the farther we look into space, the farther we look into the past. And from our perspective, the back of the planet is located further in space than the front of the planet. The image that we receive from the back of the planet has taken longer to reach us, so we see it as it was in the past, even if it is contracted. The planet does not look like it because we receive the image of its back with a delay. Rather than contracted, it appears to be rotated. This is a phenomenon we have already seen, Terrell-Penrose rotation. When we move very fast and look to our side, the edges of the object around us seem shorter in the direction of motion. This can be interpreted either as length contraction or as a rotation, as a change in perspective. For the same reason, a person watching us zoom by would not really see our ship contracted but rather rotated on itself. Over time, our field of view continues to speed of light contract. It intensifies in front of us while going completely black behind us. By accelerating more and more, we would perhaps expect to reach the speed of light at some point. What would we see then? This question might be one of the most fundamental in relativity. The answer is no. Even if the ship accelerates constantly, we will never reach the speed of light. That is because the speed of light is absolute. You may try to catch a light ray, but from your point of view, it will always escape at the same speed, the speed of light. You may accelerate as much as you wish, even if from Earth, you would seem to approach the speed of light, from your point of view, you are still motionless, and light escapes inexorably. In short, it is strictly impossible to exceed or even reach the speed of light. At best, our ship will continue to accelerate forever, and our field of vision will continue to shrink ever more until forming an infinitely bright spot in front of us surrounded by a completely black sky. Almost at light speed, all optical effects would become extreme. As we catch up with light rays before us, they all seem to come from the front. Meanwhile, the rays behind us can never reach us. In our frame of reference, the universe would be extremely contracted, like a thin fabric that we would cross from side to side in a fraction of a second. For a person on Earth, we'd be moving at the speed of light, but for us, the trip seems instantaneous. We move infinitely fast. To conclude, nothing can ever move faster than light through space, but there might be a way to circumvent this rule. In fact, nothing prohibits space itself from moving faster than light. Indeed, the theory of general relativity teaches us that the fabric of spacetime is dynamic, it can bend in multiple ways. We could thus imagine creating a bubble around our spaceship, which we would propel faster than light. This is called a warp drive in reference to science fiction. It would no longer be a matter of zooming a vehicle through space but of propelling the fabric of space itself. Our ship would remain motionless, surfing on a wave of faster-than-light spacetime. Such a structure may seem absurd and, indeed, it is currently thought to be impossible to achieve. Producing a warp drive would require bending spacetime with huge amounts of negative mass, a form of matter that does not seem to exist in our universe. That said, mathematics still allow us to model and calculate what we would see in such a situation. If we looked from outside, the warp drive would seem to appear out of nowhere. The curvature of spacetime deviates the trajectory of light rays, forming a moving lens which splits into two, one part moving forwards and the other retreating in the opposite direction. Light travels slower than the warp drive itself. When it approaches, light has not yet had the time to reach us, and after it crosses us, we receive both the light which had not yet reached us and the rays which were emitted later. Looking from the inside of the warp drive, we would see the sky contracted in front of us and very bright. Behind us, the universe would look extremely dark, and a whole patch of the sky would simply vanish from our view. The light emitted from there is too slow to catch up with us, a cone of the universe remains permanently invisible,